Hello everyone, welcome back. In this video, we're going to talk about limits and continuity, and to get this discussion started, I would like to jump right into an example. And in this example, I want us to consider the function f of x comma y, which is defined by the equation where in the numerator we have x squared minus y squared, and in the denominator we have x squared plus y squared. So the first thing I want us to think about for this function is what is the domain of this function? And so remember, the domain of a function is going to be the set of all inputs, now kind of ordered pairs, x comma y, where this equation kind of can make sense and can be evaluated. So we really have to watch out for things where we can break the function or the equation. And in this example, the thing that can kind of go wrong in the equation is potentially we could have division by 0. So we have to make sure that our denominator, x squared plus y squared, is not equal to 0. So that is really the only issue or point we have to avoid for this function. So our domain is probably best described as all the points x comma y where x squared plus y squared is not equal to 0. And well, that's only going to occur when x and y are both equal to 0. So our domain is going to be the set of ordered pairs or points x comma y such that x and y are not both equal to 0. So as long as we are not the point 0, 0, we will be a point that is in the domain of this function, and that is going to be a point that we could plug into our equation and evaluate to get an output. Okay, so the point 0, 0 is not in the domain of our function, and our function is undefined at the point 0, 0. But the next question we might consider is what happens to our function as we get closer and closer to this point 0, 0 or the origin? Or in other words, what is the limit of this function as we approach 0, 0? And so the question we are now considering is what is the limit as the input to our function, the point x comma y, approaches the point 0, 0. So we'll write down our more formal definition of a limit in just a couple moments, but first I want to explore this concept through this example. And we are going to use some of the same ideas that we used for limits for functions of a single variable. Right, when we looked at like the limit as x approaches a of a function f of x, the kind of things we would consider are how can we evaluate this limit or find this limit algebraically, numerically, and graphically. And we're going to try to consider all those same things now for our multivariable functions. And so when it came to our functions of a single variable and limits of those functions of a single variable, we had like the limit as x approaches a of f of x, and we had to think about what happened to the output of our function as x got closer and closer to a from either side. And we still have to do something similar here. However, it is a bit more complicated. And so what really complicates the situation here for these limits of functions of two or more variables is now there's more than just two directions at which we could approach the point of interest. Instead of just approaching 0, 0 from the left or 0, 0 from the right, we could also approach it from above or from below or from any angle really. And so remember, for our functions of a single variable, when we were looking at those two-sided limits or limits from all sides, we had to make sure that the limit from the left and the limit from the right were the same or that they were in agreement in order for that limit to exist. The same thing is going to happen here for our functions of several variables, but now the limit is going to have to exist and be the same no matter which direction we approach the point from. And so like I mentioned earlier, we want to try to think about being able to find our limits graphically, numerically, as well as algebraically. And so, well, graphically, we can just graph our function f of xy equals x squared minus y squared over x squared plus y squared. And if we take a look at the graph of our function, we can see some really weird behavior is going on at the origin or at the point 0, 0. Right, if we change our perspective and move the picture of our surface or function around, we can see that depending on the direction at which we approach 0, 0 from, we're going to get different output or limit values for our function. So using the graph of the function, we can see that as we approach our point of interest 0, 0 from different directions, our function is approaching different values. And for that reason, we would say that this limit does not exist. And so if we are able to graph our function, we can look at the graph of our function to see if it is going to have a limit value. However, sometimes we don't have access to that kind of technology, or the graph is very difficult to read an accurate value from. So we might try to find a limit numerically or algebraically instead. And so if we did want to find this limit numerically, the way we could do it is by creating a bunch of different sequences of points that are getting closer and closer to 0, 0. So this would be a lot more complicated and involved in the sequences we had to create and use in Calculus 1 when we were trying to find limits of a function of a single variable. And that's because, well, now we have to create a bunch of different sequences that are approaching 0, 0 from a bunch of different directions. It's really not enough just to check one or two directions for finding these limits of functions of two variables. We really have to check several directions in order to kind of be confident that the limit does exist. Even then, that's not proving that the limit will exist, but for our purposes, that's pretty much as far as we're going to go. We're not going to spend too much time or focus really rigorously proving these limits of functions of two or more variables. The reason why we're interested in these limits at all is to help us understand the idea of a partial derivative that is coming up pretty soon. So anyway, back to the discussion. If we did want to find this limit numerically, we have to create a bunch of sequence of values of different ways to approach the point 0, 0, evaluate our function at all those different points, fill out a big grid or table, and see what is happening. But we get the same result, that this limit is not going to exist at the point 0, 0, because what we'd see if we did construct that table is, depending on the direction we approached, our function would have outputs approaching different values as we got closer and closer to 0, 0. Only if all those values were the same would we say that the limit exists, and we would say that it exists as that limit value. All right, so we've seen how we can find the limit graphically. We've discussed how to find it numerically. Now let's go ahead and talk about how to find this algebraically. And so all those kind of algebraic limit laws you learned for single variable functions still carry over and apply for functions of two or more variables. So we still have things like the sum and difference rule, the constant multiple rule. All those little limit laws are still applying for our functions of two or more variables. The big difference is, well, now we can approach our points from any direction, not just left or right, but also up, down, or diagonally. So from our other approaches for this example, we are sure that this limit is not going to exist. Now we just want to verify that algebraically. And so the way we do that is by manipulating our limit currently and thinking about taking a certain path to our point of interest. And by doing that correctly, we'll be able to rewrite our limit not as a limit of two variables, but as a limit of a single variable. And then we can use our previous methods for finding the limit of a single variable function. So remember, we're trying to see what is happening to the output values or the z values of our three-dimensional surface or our function f of x comma y as our inputs are getting closer and closer to the origin or point 0, 0. And so there's lots of ways we can approach our point 0, 0. One way that we'll check out is, what if we approach it along the y-axis? So what if we took a path to the origin or the input 0, 0 that was strictly on the y-axis? Well, if we did take this path, then what we would know is that if we are on the y-axis, then x is always equal to 0. So now if we set x equal to 0 in our limit, it's going to simplify to a limit of a function of a single variable, and we can evaluate it using our previous techniques. So if we look at our limit here, we're looking at the limit as x comma y approaches the point 0, 0, but we're assuming that we're on the y-axis where x is always equal to 0, and that means really we're not looking at the limit as x comma y approaches 0, 0. We're looking at the limit as just y approaches 0 because x is already equal to 0. And so the limit as y approaches 0 of our function x squared minus y squared over x squared plus y squared. But remember, x is equal to 0. So this is going to be the limit as y approaches 0 of 0 minus y squared over 0 plus y squared. And so, well, before we take the limit, we can simplify the function here, or the fraction, and write this as the limit as y approaches 0 of negative y squared over positive y squared. But those factors of y squared will cancel each other out, and we'll get the limit as y approaches 0 of negative 1. And well, the limit of a constant is the constant. So what we see here through this algebra is that if we are approaching our point 0, 0 on the surface of this function, and we are getting closer to that point by traveling along the y-axis, either from above or from below, then our function is going to be getting closer and closer to the value of negative 1. But this is not the only path that we can take to the origin or the point 0, 0. Another way that we can approach the origin is diagonally through a line like y equals x. And so how do we incorporate into our limit notation that we are approaching this point through the line y equals x? Well, what we know is if we are on this line y equals x, well then x and y are completely interchangeable. So instead of writing our limit as the limit as x comma y approaches 0, 0, we can write it as the limit as x approaches 0. Well, now that we're having just x approach 0, we've said that y is equal to x, so all the y's can be replaced with an x. So our numerator will become x squared minus x squared, because on this path, y is equal to x. So we have x squared minus x squared up above, and then down below we have x squared plus x squared. But now if we try to simplify our limit, we're going to get a different value than our first path, right? So the x squareds in the numerator cancel out, giving us the limit as x approaches 0 of 0 over 2x squared, but that'll be equal to the limit as x approaches 0 of just 0. And again, that limit is going to be equal to the limit of the constant 0. And now we can already see that our limit cannot exist because, well, if we approach 0, 0 from the y-axis when x is equal to 0, it looks like our function is going to be equal to -1. And if we try to approach our point 0, 0 along this diagonal line through the line y equals x, we can see that our function is going to approach the output of 0. And so we can stop here because we have reached the contradiction that we were looking for. We've shown that the limit is not the same depending on the different directions we approach. But just for the sake of more practice and to see this example illustrated, let's go ahead and check out evaluating our limit from another direction. So we've come through the y-axis, we've come through this diagonal line, y equals x. We could also go through like a parabolic line like y equals x squared. But for our last example here, let's just go ahead and travel or approach our point 0, 0 along the x-axis. And so if we want to approach 0, 0 through the x-axis, well then y has to always be equal to 0. And so what happens to our multivariable limit if we start by setting y equal to 0? Then it turns into a single variable limit, the limit as x approaches 0 of x squared minus 0 over x squared plus 0. Right, and to find this, we just set y equal to 0 in our function, and now our two variable limit is a single variable limit. And so we can go ahead and evaluate this pretty quickly. It becomes the limit as x approaches 0 of x squared over x squared, but x squared over x squared simplifies down to 1, and now we just have the limit as x approaches 0 of 1, but a limit of the constant is equal to that constant. And so if we go ahead and bring up again the graph of our three-dimensional surface or the function x squared minus y squared over x squared plus y squared, we can kind of visualize these three different paths that we can take to the origin. And depending on the path we are taking, our function is approaching a different value of -1, 0, or +1. In order for a limit to exist for a multivariable function at a point, then the limit has to be the same no matter which direction we approach that point from. Alright, so we've already said this definition out loud a couple times, but let's go ahead and write it down and make sure it makes it into our notes. So we write the limit of f of x comma y as x comma y approaches a, b is L. If we can make our function f of x comma y as close to this output number L, or this z value of L as desired, by making our input x comma y sufficiently close to, but not equal to the point of interest, a comma b. Again, this is really the same idea as it was in single variable calculus. The biggest difference is, well, now we have to be careful because we can approach our point of interest from infinitely many directions or angles instead of just from the left or from the right. So we just got through the definition of what it means for a function of two variables to have a limit. Now let's go ahead and quickly talk about what it means for a function of two variables to be continuous at a point. And while it's a pretty short conversation, it's basically exactly the same as what it means for a single variable function to be continuous at a point. So we say a function f of x comma y, or a function of two variables, is continuous at the point a comma b if the limit as xy approaches a, b of our function f is equal to f of a comma b. So if we very carefully take this limit from all directions of our function as it approaches a comma b, if that limit value is the same for all directions and it's equal to a finite constant number, the same number that we would get out of our function if we just plugged a and b in, then we say that the function is continuous at that point. And so if we're interested in our function being continuous over some set of points like the domain, well then it just has to be continuous at every single point a comma b in that set. In this example, we are given the function f of x comma y, which is defined as 3x squared times y divided by the quantity x squared plus y squared. And in this example, we're trying to find the limit of our function as x and y approach the point 0, 0, or we want to show that this limit does not exist. So in order for a limit to not exist, we have to show that as we approach this point 0, 0 from a couple different directions, our function is approaching different values. Or if we think the limit does exist, what we have to show is that as we consider a bunch of different directions in which we can approach the point 0, 0, through all these directions, no matter which path we take, it looks like our function is approaching the same value. And so we're not going to be too rigorous in this example and trying to check all the infinitely many directions. We're just going to check like 4 or 5 directions, and if they all are in agreement, then we'll say that's good enough and we have good enough reason to believe that the limit exists. All right, so let's go ahead and figure out how we're going to approach the limit values. So we can think about visualizing our point of interest as a point in the xy plane or the domain of our function. And so once again, we are approaching the point 0, 0. And so we could start by approaching our point 0, 0 along the x and y axes. So say we want to approach our point 0, 0 for this function along the x-axis. Well then, if we are approaching 0, 0 along the x-axis, then y will be equal to 0. And we can take the limit as x approaches 0 of the same function, but with the substitution made that y is equal to 0. Well, if we set y equal to 0, our numerator is going to have a factor of 0 and all get multiplied to 0, and our denominator will just be x squared. So if y is equal to 0 and we're on the x-axis, our function turns into 0 over x squared. And instead of taking the limit as x and y approach 0, 0, we can look at the limit as just x approaching 0. And well, what happens to 0 over x squared? Well, before we even take the limit, we know that 0 over x squared simplifies to 0. So then if we try to take the limit as x approaches 0 of 0, we get the constant 0. Okay, well maybe we'll get a different value if we approach 0, 0 along our y-axis. And so, well, if we're approaching 0, 0 along our y-axis, either from above or from below, it's going to require x to be equal to 0. And if we set x equal to 0 in our limit is going to simplify to a easier to work with limit. So if x is equal to 0, then it's not moving, and the only thing that is varying is going to be y, so just y will be approaching 0. And if x is equal to 0, we're going to have something similar happen. Our numerator is going to get a factor of 0 squared, and our denominator is going to simplify now to just y squared. So our multivariable limit simplifies to the single variable limit, and that limit will simplify even further to just the limit as y approaches 0 of 0. And again, the limit of a constant is the constant. So no matter which axis we approach the origin from, this function is approaching the value of 0. That's looking pretty good, but we've only really checked 2 directions, and there's infinitely many left to go, but we're not going to check all of them. But let's check at least 2 or 3 more before we try to get confident that the limit is equal to 0. So let's go ahead and try to check what happens to the output of our function as we approach the origin from the diagonal line y equals x. And so this isn't the only diagonal line we could use. We could also use y equals 3x, y equals 2x, or any line that goes through our point. Lots of these examples will use the point 0, 0, but if you're at a different point, then you have to change the equation for your line or whatever path you are taking to make sure that that function or equation that describes your path actually passes through the point of interest. Well, whenever we are on the line y equals x, we can make the substitution where we replace each y with an x or each x with a y, and we'll either be looking at the limit as x approaches 0 or as y approaches 0, depending on which of those 2 substitutions we make, but they should be equivalent. So let's go ahead and replace all the y's with x's. Then we'll be looking at the limit as x approaches 0 of our modified function instead. So if y is equal to x, then in the numerator, we don't have 3x squared, we have 3x cubed. And in the denominator, instead of x squared plus y squared, we're going to have x squared plus x squared, or 2x squared. So our multivariable limit has now turned into the limit as x approaches 0 of 3x cubed over 2x squared, which we can simplify as the limit as x approaches 0 of 3/2 times x. Now it's not the limit of a constant anymore, but it's the limit of a very simple function, a function that is continuous at 0. And so we can find this limit just by plugging in x equals 0. And what do you know? Again, we get 0 as the value our function is approaching. And so we're probably feeling pretty good that the limit of this function is going to be 0 as the input approaches 0, 0. But let's go ahead and check just one more path. Most of the time, the paths we take are these straight line paths, but they do not necessarily have to be straight lines, but they're the easiest to check. We could even take some weirdly curved path like a parabolic path. As long as the curve that describes our parabola goes through our point of interest, this can be done. So let's go ahead and mess around with the curve y equals negative x squared. That's a parabola that is going to go through the origin. And so now if we replace every y with negative x squared in our equation, it'll be as if the inputs of our function are approaching 0, 0 along this parabolic path. All right, so if we're on the path where y is equal to negative x squared, or we're on this flipped over parabola, then what is going to happen to our limit? Well, we can write it as the limit of a single variable function using just x now, because we'll replace each y with negative x squared. So our factor of y in the numerator is going to be replaced with a negative x squared, and that will give us a negative 3x to the fourth in our numerator. And in our denominator, our y is going to be replaced with a negative x squared. So that'll make our denominator x squared plus x to the fourth, right? That y squared is going to be a negative x squared, and negative x squared times another negative x squared is going to give us positive x to the fourth. And so now we have a much simpler limit to work with. And the best way to evaluate this limit is to cancel out the greatest common factor of x squared. If we do that, we can rewrite it as the limit as x approaches 0 of negative 3x squared over 1 plus x squared. And so now we can find this limit using direct substitution. Plug in x equals 0 everywhere. And we end up with 0 over 1, which simplifies to just 0. No surprise by now that this limit value is equal to 0. We should be pretty confident at this point that the limit of our function is in fact 0. And so we've done this purely algebraically just by approaching our point of interest through these different paths. If we go ahead and take a look at the graph of our function, we're going to see this same exact thing happening. No matter which path we take as we approach the point 0, 0, our function is approaching the output or z value of 0 as well.